Today we're going to continue to discuss linear mappings between linear spaces, and the first thing that we will discuss is the space of linear mappings. Check the numbering. Yeah. So let V and U be two vector spaces over the same field. And consider the set of all linear mappings from V to U. I will denote it as follows. So hom V U. So this is the set of all mappings from V to U such that F is linear. Once two linear mappings are given, then we can continue. We can consider the sum of these two mappings, and we can multiply linear mappings by scalars. So let F and G be two elements of this set. Then, by the definition, F plus G, it is also the element of this set. So I'm going to apply it to a vector from the first space, and by the definition it is just F of V plus G of V for all V from V. So obviously this is also a linear map. And in the same way, I'm going to multiply lambda. I'm going to multiply a linear mapping by scalar, and so in order to define this product, I will set this to be equal to lambda multiplied by F of V for all V from V, and for every lambda from the field. So obviously F plus G belongs to this space of linear mappings, and lambda multiplied by G also belongs to this set. And I will formulate the proposition, which is quite obvious. So hom V U is a vector space over the same field. So the proof follows from the properties of linear mappings, and so the operations are defined here. So I will just write down that from the properties of linear maps and from the fact that both V and U are vector spaces over F. So I will not check all the properties carefully, so this is more or less obvious. So we get a linear space of linear mappings from V to U, and another important result is that this vector space is isomorphic to the space of matrices. So let E1, etc., Em, and F1, etc., Fn be bases in vector spaces U and V respectively. Then the mapping psi capital from the space of linear mappings from U to V to the space of n by m matrices with entries from the field defined as so this map sends every linear mapping to its matrix with respect to these two bases. With respect to the bases E1, etc., Em, and F1, etc., Fn. So the mapping is an isomorphism. So we have two different vector spaces over the same field, and so we claim that this mapping is an isomorphism. So obviously psi is a linear map. So if we consider the sum of two linear mappings, then the matrix of this new linear mapping is obviously the sum of the matrices of these two linear mappings. This easily follows from the definition of the matrix of a linear mapping. So psi is a linear mapping. And now let us consider its kernel. So if f belongs to the kernel of psi capital, then AF is 0, so this is the zero matrix, and this means that every vector from the basis E1, etc., Em goes to 0. And so this is equivalent to the fact that f is 0. So the kernel of this mapping is trivial. And the only thing that is left is the surjectivity of this mapping. So consider a matrix A with entries A sub ij from the space of n by m matrices with the coefficients, with the entries from our field. And now I'm going to define the corresponding linear mapping. So define f from V to U. So for any vector v from this space, where v is the sum x1 times e1 plus etc. plus xm times em. So we are going to set f of v to be equal to the sum where j ranges from 1 to m x sub j times the sum where I ranges from 1 to n a sub ij f sub j. So this is a linear, so this defines a linear mapping from the space V to the space U. And so obviously these are the images of the vectors of this basis, and so when we define our mapping like this, then f of E sub j is the sum where I ranges from 1 to n a sub ij fj, and therefore the mapping of this, the matrix of this map is exactly what we need. This is exactly the matrix A. That's why psi is surjective. And this proves that psi defines an isomorphism between these two vector spaces. This is quite simple, but nevertheless I decided just to write everything in details. And now I need to make a remark. This isomorphism depends on the choice of a basis, or better to say on the choice of basis, because we have two different bases in two different spaces. So in this sense, this isomorphism is not canonical or is not natural, as we will call it later. But nevertheless, we have these two mappings. So, and from this, we conclude that in case of finite dimensional spaces, the dimensions of these two spaces are equal. So let me write this down as a corollary. So if M is the dimension of V and N is the dimension of U, then the dimension of the space of linear mappings from V to U equals N multiplied by M. It follows from the fact that this is the dimension of the space of matrices. So this is one very important space, and then let us consider some particular space, some particular case. So another remark. If U equals V, then the space V is usually denoted as the space of endomorphisms of V. And in this case, we always consider one basis instead of two different bases. What does this mean? So if the second vector space is the same as the first one, then just initially we can take two different bases in the same space, but when we restrict ourselves with this particular situation, when the second space is the same as the first one, we always choose the second basis, the basis f1, etc., fm, the same as the first one. And so in the when we talk about fixing some basis for a linear operator, so this is the space of linear operators, then we always assume that the second basis is the same as the first one. So these are just the definitions, and now let us discuss some properties of this correspondence between linear mappings and matrices. So 5.7. Now I will use a stylish word, functoriality. So this word describes the properties of this kind when people talk about category theory. So we will not go into the details, but I will just use this stylish word in order to describe the properties that we'll discuss a bit later. So first we will start with one remark. So consider the space of endomorphisms. Then psi of the identity map is the identity matrix. Where ID is the identity mapping. So it maps every vector to itself. This is more or less obvious, but here we need to take into account that we fix two equal bases in this vector space, and we consider the matrix with respect to the pair of bases which are the same. So this is quite trivial, and then another proposition. So that V, U, and W be vector spaces over the field F. So let F be a linear mapping from V to U, and G be a linear mapping from U to W. So we consider two linear mappings, and we have three spaces, and we can consider the composition of these two linear mappings. So fix basis E1, etc., EM, F1, etc., Fn, and G1, etc., Gk in V, U, and W respectively. So once we fix this basis, we can write down the matrices of these mappings, and the claim is that in this case the matrix of G composition with F equals the product A of G by A of F. So here, these are the matrices of the mappings F, G, and the composition with respect to appropriate basis. So let us prove this statement. So we need to denote somehow the elements of these matrices. So let AF be the matrix that consists of elements A sub ij, AG be the matrix that consists of elements B sub ij, and a G composition F would be the matrix that consists of elements C sub ij. So take a vector V, that is the sum where j ranges from 1 to n, x sub j, e sub j from the first space, and consider the composition of F and G applied to this vector. So G composition F applied to V is equal to G of the sum where j ranges from 1 to n, x sub g, by f of e sub j. So I'm using the property of linearity here, and now I can write down the coordinates of this vector using the fact that we know the matrix of this mapping. So we get x sub j by the sum where I ranges from 1 to n. Sorry, it should be m here because we have m vectors in the first basis. So the sum where I ranges from 1 to n of a sub I j by f sub I. So this follows from the fact that these are the elements of the matrix of the first mapping with respect to the pair of bases that we fix. So then I continue this relation, so I get the sum where j ranges from 1 to m, x sub j, the sum where I ranges from 1 to n, a sub ij by g of f sub I. So this is what we get, and now we apply this mapping to a vector from the basis that we chosen in the second space. So we get the sum, another sum, a sub ij by the sum where L ranges from 1 to k, where k is the dimension of the third space, and here we put b sub Li by g sub L. So this is what we get, and now I need to change the order of summation. So first I write the sum over L, then I put the sum over j, sorry, and then I put the sum over I, and here we get b sub Li by a sub ij, and the whole thing is multiplied by g sub L. So I deliberately changed the order of A and B just in order to notice that this is nothing but the product, the element of the product of the two matrices. So this is the lth, jth element of the product of the corresponding matrices. So AG by AF, the lth, jth element. Okay, so this is what we get when we apply these two mappings just one by one. And now let us apply the composition. So on the other hand, g of f applied to V is just the sum where j ranges from 1 to m, x sub j, g composition f applied to E sub j. And when we apply the composition, we need to write down the elements of the matrix of the composition. So we get x sub j by the sum where L ranges from 1 to k. And here we get the elements of the matrix of composition, so they are denoted by C, C sub L j multiplied by G sub L. So this is what we get, and I need to change the order of summation. So here the first summation would be over L, then another summation over J, and here we have C sub L j by G sub L. So this is what we get. And since V is arbitrary, these matrices are equal. So C sub Lj equals A G A F Lj element. So this is just what we get. So it follows that the matrix of the composition equals the product of these two matrices. This is exactly what we needed to prove. So here I will finish the part of the section that deals with linear mappings, and the next section would be about the dual space, or the space of linear functionals. So section number 6, dual space. And so 6.1, linear functionals. We have already introduced this notion, so a linear functional is a linear mapping from a vector space to the field, which is considered as one-dimensional vector space over itself. So let us give the definition. The space of all linear mappings functionals, as we already said, linear mappings from V to the field is called the dual space. And there is the standard notation V star. So V star is the space of all linear functionals. And now let us consider some examples of linear functionals. So we already know that this is a vector space. It follows from what we just discussed, because here the second vector space is just a field, which is one-dimensional vector space over itself. So consider several examples of linear functionals. So A maps to the trace of A, defines a linear functional on the space of square matrices with entries from some field. So obviously this is a linear functional, linear mapping. And maybe one more example. So consider the space of all continuous functions on an interval AB. So V is CAB. Then F, then F to the integral f of x dx defines, this correspondence defines a linear functional on C of A, B. So here f is a continuous function, and so we integrate this continuous function over the interval from A to B. We get some number, and so we get a real number, and we get some linear functional from the space of continuous functions to the space of real numbers. And of course this function, this vector space is infinite dimensional, but so we have an example of a linear functional on an infinite dimensional space. And now I'm going to prove a very simple property that for every non-zero linear functional xi, it's the dimension of its kernel the dimension of the kernel of Xi is n minus 1, where n is the dimension of the space V. So here we consider finite dimensional vector spaces, and so the dimension of the kernel of every non-zero linear functional is n minus 1. So let us prove this simple result. So if Xi is non-zero, then there exists some vector v from V and some element A from the field, such that Xi of V equals A, and A is non-zero. So if Xi is the zero linear functional, then the image of every vector is 0. So here there exists such a vector and such element A, and therefore the image of Xi as a linear mapping coincides with the whole space, just because the image is always a vector space, and if this vector space contains some non-zero element, then it contains every element that is proportional to its to this element, and that's why it contains the whole one-dimensional space. So the image is the whole space, and that's why the dimension of the image of Xi is 1, and we have the relation between the dimension of the kernel and the image of every linear mapping. So the dimension of the kernel of Xi equals the dimension of V minus the dimension of the image of Xi, and so we have n minus 1. So this is quite trivial, but nevertheless at some point this proposition can be useful. So now we will discuss the dual basis. In general, we need to understand the structure of the dual space, and the simplest way to do this is to choose some basis in our vector space V, and then to introduce some special basis in the dual space that is related to this basis. So let n be the dimension of the vector space V, and consider a basis E1, etc., En in V. Consider a linear functional epsilon sub I from the dual space, such that epsilon sub I of V equals x sub I, where V is the sum where j ranges from 1 to n of x sub I, x sub j, sorry, E sub j. So what does this mean? We consider a basis in our space. We consider the expansion of a vector with respect to this basis, And we define a linear functional that takes the ith coordinate of this vector with respect, which takes the ith coordinate of every vector with respect to this particular basis. So here I changes from 1 to n, so we get n different linear functionals. And so obviously epsilon sub I is a linear functional. Fine. And these coordinates, these functionals, are sometimes called coordinate functionals. Just because they assign to every vector its coordinate with respect to some basis. And note that epsilon sub I of E sub j is delta sub ij, so I will just explain this notation, which is 0 if I is different from j and 1 if I equals j. So this is the standard notation. This is called the delta, the Kronecker delta. And it is very convenient to use this symbol when dealing with linear functionals, and we will see how to use it further. So it obviously follows from the definition of these functionals that epsilon sub I of E sub j is exactly delta sub ij. And now I'm going to formulate and prove an important theorem that for every basis E sub 1, E sub n in the functionals epsilon sub 1, etc., epsilon sub n form a basis in the dual space. So we need to prove two different things. First, we need to prove that these vectors are, these elements are linearly independent. And secondly, we need to prove that every linear functional can be represented as a linear combination of these coordinate functionals. So assume epsilon 1, etc., epsilon n are linearly dependent. Then we have this linear combination which is equal to 0. And what does this mean? This linear combination is equal to 0 as a linear functional. So this is the 0 linear functional. This means that if we apply it to any vector from V, we get 0. And in particular, apply this linear combination of functionals to E sub j, to a vector from the basis that we consider. So according to these properties of linear functionals, we get the sum. So let me just write it in details. So we get the sum where I ranges from 1 to n, alpha sub I, epsilon sub I of E sub j. And so here I use this Kronecker notation. So we get the sum where I ranges from 1 to n, alpha sub I by delta sub ij. And so we get alpha sub j, just because the only non-zero term in this sum is the term where I equals j. And so this is 0, just because the value of any just because the value of this linear functional on every vector is 0. And so this is 0 for every j from 1 to n. And so the linear combination is trivial, and that's why these functionals are linearly independent. And the second thing that we need to prove is to show that any linear functional can be expressed as a linear combination of these functionals. So consider an element of the dual space. So consider xi from V star and denote lambda sub j, the value of xi on the vector of the basis that we consider. So for all j from 1 to n. And consider another linear functional. Consider eta from the dual space that is defined as a linear combination, or as the linear combination of these functionals with these coefficients. So eta is lambda 1 by epsilon 1 plus etc. plus lambda n by epsilon n. So we get such a linear functional, and we will show that xi equals eta, and this will prove that we get a basis in our dual space. For every j from 1 to m, so eta of E sub j is the sum where I ranges from 1 to n of lambda sub I by epsilon sub I of E sub j, which is the sum where I ranges from 1 to n lambda sub I delta sub ij, which is exactly delta sub j. But according to our definition, delta sub j is nothing but the value of xi on the vector E sub j. So we prove that xi and that eta and xi map any vector from the basis to the same element. So they coincide on every vector from the basis. That's why xi equals eta. And this proves that that every vector from the dual space can be represented as a linear combination of the vectors from epsilon 1, etc., epsilon n. So this proves that we get a basis. And now we can formulate the following definition. The basis epsilon 1, etc., epsilon n is called the dual basis in the dual space. So this basis is dual to the initial basis in our vector space V. And so we see that the number of vectors in the dual basis is the same as the number of vectors in the initial basis. So as a corollary, we get the fact that the dimension of the dual space is the same as the dimension of the initial space in case of a finite dimensional space, and that's why if V is finite dimensional, then the dual space is isomorphic to V. But so I need to make a remark that this isomorphism depends on the choice of a basis, because this isomorphism, the existence of this isomorphism follows from the fact that the number of vectors in a basis in the second space is exactly the same as the number of vectors in the first space. And so this is the first remark, and the second remark is that if V is infinite dimensional, then dual space is always, in some sense, larger than V. So I will not explain what does this mean, because here we study only finite dimensional spaces, but this works only in case of a finite dimension. And the next thing that we need to discuss is the relation between the changes of basis in the space and in its dual. So change of basis in the dual space. So let us formulate and prove the following theorem. So let E1, etc., En and E1 prime, etc., En prime be two bases in a vector space V. So let C be the change of basis matrix from the first basis to the second basis. Then the change of basis matrix from epsilon 1, etc., epsilon n in the dual space to the dual basis epsilon 1 prime, etc., epsilon n prime is c to the minus 1 transpose. So this is what we need to prove. We consider two bases in the space V, and we consider corresponding dual bases in the dual space. And we need to prove that the change of basis matrix from the first basis in the dual space to the second basis in the dual space is c to the minus 1 transpose. So let us prove this result. So consider a vector so this is the expansion of this vector with respect to the first basis, and now I'm going to consider the expansion of this vector with respect to the second basis. So we have these two bases, and now let us fix some index I and apply the corresponding vector of the dual basis to this vector. So then epsilon I of V equals just x sub I, because this is the coordinate functional, and we know the relation between the coordinates of a vector with respect to two different bases. So this is the sum where j ranges from 1 to n, c sub ij multiplied by x sub j prime. So the old coordinates, the coordinates with respect to the old basis, are expressed in terms of the coordinates with respect to the new basis. And here C is the change of basis matrix. So these are the elements of the matrix C, which is the change of basis matrix. Fine. And then this is the jth coordinate of our vector with respect to the second basis. So we can rewrite this as the sum where j ranges from 1 to n, c sub ij by epsilon prime sub j of v. And this works for every vector v. So since v is arbitrary, we get the relation between functionals. So epsilon I equals the sum where j ranges from 1 to n, c sub ij epsilon j prime. So this is what we get, and we get the relation between the expansion of the functional epsilon sub I in terms of functionals epsilon prime sub j. And so the coordinates of epsilon sub I with respect to the basis, to the primed basis, are exactly in the ith column of C. So we see that the matrix C transpose is the change of basis matrix from the primed basis to the unprimed basis. Just because we express vectors of the unprimed basis in terms of the vectors of the primed basis. And that's why the change of basis from unprimed to primed basis is the inverse one, so is C to the minus 1 transpose. This is exactly what we need to prove. So we get the relation between so if we know the relation between the two bases in the space V, then we automatically get the relation between the corresponding dual bases in the dual space. And the next thing that we are going to discuss is the double dual space. So let us start with the definition. The space V star star, which is the space of linear functionals on V star, is called the double dual space. So sometimes it is denoted just as V with two stars, or sometimes it is also called the bidual space. So what does this mean? Maybe this is not the thing that is just very easy to understand immediately, but there is nothing difficult. So we have a vector space, then we consider the vector space of all linear functionals on V. This is also a vector space that has the same dimension as V, as we know in finite dimensional case. And so we can consider linear functionals on the space of linear functionals. And this space is called the double dual space. And so let us make a remark. If the dimension of V is finite, then the dimension of the double dual space is equal to the dimension of the dual space, just because it is the dual space to the dual space, and it is also equal to the dimension of the initial space. And all these vector spaces are isomorphic. But this isomorphism is not natural, because in general these isomorphisms are not natural. Just because we claim that these spaces are isomorphic, because they have the same dimension. But it appears that there is one special isomorphism between the space V and its double dual, which can be constructed without using any basis. And we'll discuss this just in a moment. Now I'm going to formulate a very important theorem. The theorem about the natural isomorphism between any vector, any finite dimensional vector space, and its double dual. So let V be a vector space, and assume the dimension of V is finite. Then the mapping psi capital from V to its double dual defined by the following relation. So we take psi of V, and we want psi of V to be the element of the double dual space. So we need to explain how this linear functional acts on linear functionals. So we need to apply it to a linear functional, and we write down something very natural. So in fact, this is the only natural thing that can be written here. So the most natural thing. So then the mapping defined by this formula for every V from the space V and for all psi from the dual space. So then this mapping is an isomorphism So let us prove this result. And in fact, we need to prove many things here. First of all, we need to prove that psi is well defined. So we need to prove that psi is a linear mapping on V star. So psi of V is a linear functional on the star. So psi of V, so we're going to apply psi of V to a pair of linear functionals. So according to our definition, we get psi of V plus eta of V. So psi of V is psi capital of V applied to psi, and this guy is nothing but psi capital applied to, of V applied to eta. So this is just the property of linearity of psi of V. And similarly, psi of V applied to alpha by psi is, according to our definition, this is equal to alpha multiplied by psi of V, which is nothing but alpha multiplied by psi capital of V applied to psi. So this works for all psi and eta from the dual space and for every alpha from the field. So we prove that psi of V is the element of an element of the double dual space. write this explicitly. Hence, psi of V belongs to the double dual space for every V from V. Then we need to prove that psi is a linear mapping. Secondly, because when we need to prove that something is an isomorphism, we need to prove that this mapping is a linear mapping, and then we need to prove that it is injective and surjective. So why psi is a linear mapping? So consider psi capital of u plus v, and so apply it to a linear functional psi. So according to our definition, this is psi of u plus v, which is psi of u plus psi of v, because psi is a linear functional. And so the first guy is just psi capital of u applied to psi, and the second guy is psi capital of v applied to psi. And in the similar way, we need to take psi capital of alpha by v and apply it to a linear functional. So according to the definition, we get psi of alpha v, which is alpha multiplied by psi of v, according to the property of linearity. And so we get alpha multiplied by psi capital of v applied to psi. So this works for all u and v from the space V for every alpha from the field, and for all psi from the dual space. Okay, so this is the second part of the statement. And then we need to prove that our mapping psi is injective and surjective. So in order to prove that a linear mapping is injective, we need to show that its kernel is trivial. So consider the kernel of the mapping psi capital. So if V belongs to the kernel of psi capital, then 0 equals psi capital of V applied to any linear functional. So this is, according to our definition, this is psi of V, and this should be 0 for any psi from the dual space. In particular, zero equals epsilon I of V for every I from 1 to n, where epsilon 1, etc., epsilon n is the dual basis to some basis E1, etc., En in the space V. And this is the coordinate functional. So the ith coordinate of this vector is 0, for every I. So what do we get? We show that all the coordinates of this vector with respect to some basis are zeros. That's why V is the zero vector. So the kernel of this mapping is trivial. We just show that when we apply elements of the dual basis to this vector from the kernel, we get that all its coordinates are zeros. So psi is injective. But we are in the finite dimensional situation, so the dimension of the image of psi is the dimension of V minus the dimension of the kernel of psi. And this dimension is 0, so we get the dimension of V, and that's why the image of psi capital is the whole space, and that's why psi capital is surjective. So this proves our theorem. And this mapping psi is called the natural isomorphism. So definition, the mapping psi capital is called the natural or the canonical isomorphism between V and the double dual space. So let me make a remark. Natural means that its construction is independent of the choice of a basis. So this is a very essential difference between the constructions that we had before and this particular construction. So in all constructions that we had before, we proved that two vector spaces are isomorphic by choosing a basis in the first space, choosing a basis in the second space, and constructing this isomorphism by assigning the elements of the second basis to the elements of the first basis. But here we prove that we prove that this mapping is an isomorphism without choosing any basis. We just use this formula, which is very natural. So this is the only natural thing that can be written universally. So this formula works for every vector space over every field. So for example, if we put here some constant, say 2, then this formula would not be applicable in case when the characteristic of a field is 2. But this formula is universal, so it can be used in any possible situation, and that's why this isomorphism is called natural, or the canonical isomorphism between the space V and its double dual. So this means that we can identify these two spaces. So we can think of the elements of the space V as linear functionals on the space V star. So we can somehow invert this formula, and we can think of this as V being applied to psi. And this duality reflects the fact that the double dual space is, or the double dual space can be identified in the natural way with the space V. And finally, here I need to make a remark that in the infinite dimensional case, the situation is more complicated. So if the dimension of V is the infinity, then psi is an inclusion but we cannot claim that psi capital is surjective. And if psi capital is surjective, then such vector space V is called reflexive. So in the case of finite dimensional spaces, all vector spaces are reflexive, but in the infinite dimensional case, this is not true. There are examples of the spaces that are not reflexive. So we will not talk about this, but this is just to show that in the infinite dimensional case, everything is much more complicated. The next subsection would be about dual linear mapping. So let V and U be two vector spaces over the same field F. Then, so definition, let F be a linear mapping, then the mapping F star, which acts on U star and sends the elements of U star to V star, defined by the following relation: F star of of eta applied to V by the definition is eta of F of V is called the dual linear map. So what is important here, that in this construction f acts from v to u, but the dual map in some sets acts in the opposite direction. So it takes the dual space to the second space and maps it to the dual space to the first space. And so this is how this mapping is applied. So we take any element from the dual space to the second space. So this guy should be the element of the space V star. So we need to say how to apply this element to any vector from V. And by the definition, this is eta of f of V. So this works for every eta from U star and for every V from V. And note that this formula is also kind of universal, so it does not require to choose any basis or whatever. So it is just some formula that can be written down without any choice of a basis. And so the first statement that is quite trivial is that if f is a linear map from V to U, then f star is also a linear map. I will not prove this just because the linearity easily follows from the definition. So this is kind of an obvious statement. And now let us formulate and prove another statement that is not so obvious. So it describes the matrix of the dual linear mapping. So let E1, etc., EM and F1, etc., Fn be basis in vector spaces V and U respectively. So let epsilon 1, etc., epsilon m and psi 1, etc., psi m be dual basis psi 1, phi 1, phi n, because we have n elements in the second basis, be dual basis in V star and U star respectively. Let AF be the matrix of a linear mapping F from V to U with respect to the basis E1, etc., EM and f1, etc., fn. Then the matrix of f star with respect to the basis epsilon to the basis phi 1, etc., phi n, and epsilon 1, etc., epsilon m is the transpose of AF. So A F star is AF transpose. This is what we need to prove. So we have one mapping from V to U. So we fix a pair of bases there in these spaces, and then we have the matrix of this mapping. Then we have a pair of dual bases in the dual spaces, and the claim is that the matrix of the dual mapping with respect to this pair of dual bases is nothing but the transpose to the matrix of the original linear mapping. So let us prove this theorem. Consider V from V. So V is a linear combination where j ranges from 1 to n, x sub j, e sub j, where j ranges from 1 to m, because we have m vectors in the first space. And then I need to apply the vector. I need to apply the mapping f prime to some vector of this basis. So I take f prime of phi sub I, and in this case I will get an element of the dual space to the first space. So this guy acts on V. So I will apply this to V, and according to our definition, this is just phi I of f of V. So this is what we get. And now let us substitute the expansion of V here. So we get the sum where j ranges from 1 to m, x sub j, f of e sub j. This follows from the property of linearity. And now we can just write down the expansion of this vector with respect to the vectors of the second basis. So the first sum remains unchanged, and here we write the second sum where L ranges from 1 to n, and so here we put A sub L j multiplied by F sub L. So here these are the elements of the matrix of the first of the matrix of the mapping of the mapping F. So and now let us continue this computation. So according to the property of linearity, so we get the sum where j ranges from 1 to m, x sub j, the sum where L ranges from 1 to n of A sub Lj phi sub I applied to f sub L. So this is what we get. And now we need to recall that these guys are the elements of the dual basis to the elements of the first basis. So this is nothing but delta, nothing but Kronecker's delta IL. And so we get the sum where j ranges from 1 to m of x sub j by a sub ij. So this is what we get. Okay, but now let us represent x sub j as the element as the element of the dual basis, the coordinate functional epsilon sub j of v multiplied by a sub ij. So this is what we get here, and now we have the relation between the two linear functionals. So this is one linear functional that is applied to the vector v, and here we have another linear functional which is applied to the vector v. Since v is arbitrary, f star of phi I equals the sum where j ranges from 1 to m of a sub ij by epsilon sub j. So we get an expansion of the image of the vector from the basis in the space u star with respect to the basis in v star. But note that here the first index is fixed, so the ith row of the matrix IF consists of the coordinates of f star of phi sub I with respect to the basis epsilon 1, etc., epsilon m. So what do we get? We get the coordinates that are written in the row of this, in the ith row of this matrix, and not in the corresponding column. That's why the matrix of the dual mapping is exactly the transpose to the matrix of the initial mapping. So this proves the theorem. And this is rather natural construction, and there is nothing strange in this construction, just because this mapping acts in the opposite direction. So if we think of these mappings in terms of matrices, I mean if we fix some basis, so if the dimension of this space is m and the dimension of this space is n, then the matrix of this mapping is an n by m matrix. And since here we have a mapping of an n-dimensional space to an m-dimensional space, we get a matrix of the type m by n. So it is very natural to expect that these matrices are transposed to each other. And so this is exactly what we prove in this theorem. And finally, let me formulate one more proposition. I will not prove it just because it is more or less obvious that the mapping F to F star defines a natural isomorphism between the space of linear mappings from V to U and the space of linear mappings of U star to V star. So why it is more or less obvious? We just need to check. It's not obvious, but this is quite similar to what we proved before. So we need to prove that this construction defines an isomorphism between these two spaces. So we know that the dimensions are the same, so there is nothing strange that they are isomorphic, but the reasoning similar to what we had before proves that this mapping is an isomorphism. So proof similar to the proof of the previous theorem. So I will not go into the details. This is a good exercise just to repeat the proof and to see that everything works more or less in the same way in this case also. And so this is what we need to know about the dual space, the double dual space, and the dual linear mapping. So that's it for today.